right, everyone, as promised in the last section, in this section, we're going to talk about counting. But particularly, we're going to talk about how to count different outcomes in different situations, depending on what you're trying to learn about and depending on the situation that you have. So we'll talk about these as we go along, right? The first way to count different outcomes, particularly for things like independent events, is what's known as the fundamental counting principle. Okay, so if you perform some sequence of operations, right, if there's multiple events that are going to occur, then you just multiply the number of ways to get the total number of ways that you could do the sequence. Okay, you'll see some of this in the other video from a previous class that I posted in the playlist this week. And you'll do a little bit of this in the probability project this week. But I want you to kind of get the idea of how this works, right? So a certain automobile is available in any of three colors, okay, and you can either have a large or a small engine. Right? How many different ways can you choose the car? Okay, well, here you have what is essentially an outcome tree, right? If we're going to choose colors, right, there's three, right? It can be red, it can be blue, or it can be green. Okay? And then from that, we could either choose a large or a small engine, right? Or a large or a small engine, or large or small engine. So if we just, we're just going to label these with letters to make things a little easier, right? Then there are 6 possible outcomes, right? You can have a red car with a large engine, or a red car with a small engine, a blue car with a large engine, or a blue car with a small engine, okay? Or a green car with a large engine and a green car with a small engine. And we can count this way. We can do this with different types of events. Okay, but to figure out the total possible outcomes, well, it's just the 3 choices times the 2 different types of engines. 3 times 2 is 6, right? So we can get the same amount here. And you'll see this with a slightly larger example in one of the other videos and in that probability assignment. So let's use that fundamental counting principle to practice just a little bit. When ordering a certain type of a computer, you've got 3 choices for a hard drive, 4 choices for the memory, right? 2 choices for a video card, and 3 choices for a monitor. How many different ways can you order a computer? Okay, well, if there are 3 choices for the hard drive, 4 choices for memory, 2 for a video card, and then 3 for a monitor, if we just multiply all of those together, 12 times 6 is 72. That is 72 computer options. 72 different possible computers you could make with all of these different choices. And so it's just a way of counting the possible outcomes in a particular situation, given the choices that you have to make. The quiz contains 3 true-false questions, 2 multiple-choice questions, and 2 multiple-choice questions with 5 choices each. Okay, how many different sets of answers are there? Okay, well, if we're talking about answers, right, there are 3 true-false questions. True-false has 2 answers, right? So we want to multiply times 2 3 times for the true-false questions. Okay, and then there are 2 multiple-choice questions with 5 choices. So we're going to multiply times 5. Okay, and that winds up being 8 times 25, which is 200. So there'd be 200 answer sets here. Now, in the last section, I pointed out to you towards the end, we had a problem where we were multiplying numbers in order, right? 7, 6, 5, 4, so on, okay? Sometimes we have to do that in particular problems to count the number of possible outcomes, and sometimes it's just kind of easier to deal with. And so we use a particular type of notation called factorial notation in order to represent that multiplication. Okay, this is not really a math thing so much as we are just using it as a bit of a shorthand of writing these numbers out every time. Okay, and you'll see how it becomes helpful really quickly. Okay, in math, we use factorial notation to write these problems just in a more concise format. So that just means that if we write 5 with an exclamation point behind it, that's just saying that's 5 times 4 times 3 times 2 times 1. And you just count down from whatever number it is all the way down to 1. Okay, so 5 factorial will be 120. Your calculator likely has a factorial button or an option, but it may be as a second option or under, I believe it might be the math button on some of your calculators. But do look for it. It's almost certainly there. Okay. When we deal with factorials, you just have to remember that they're just multiplication problems. They are not fractions or anything like that. Okay, 4 factorial over 2 factorial, that you can't divide like this. Okay, you can't divide like this. You have to divide like this. Okay, down at the bottom. Okay, if we want to do 6 factorial divided by 2 factorial, we can't just say that's 3 factorial. Okay, that's 6 times 5 times 4 times 3 times 2 times 1. Okay, divided by 2 times 1. Now what we can do is we can reduce these. And so that the remainder will give us our answer. And that looks a lot like the problem you saw at the end of the last section. And that was why I wanted to point that out when I did. Okay, so let's just look at a little bit more about factorials, right? You should never have anything with negative numbers and factorials. This is not really going to happen. It's just a shorthand to show multiplication for numbers in order. It's not like a mathematical operation of any kind. When we have as a placeholder for particular problems, which you'll see when we're solving some of these later problems, or where you can see where it might occur, we just say that 0 factorial is equal to 1. Okay, that's just an identity thing. You just kind of have to remember that. Your calculator will tell you that as well. Okay. You can reduce factorials when the top and the bottom are the same number, right? So 100 factorial over 98 factorial. If we were to write 100 factorial out, right, that's 100 times 99 times 98 times 97 all the way down, right? But since we're dividing by 98, 98 is 98 times 97 times 96 times 95 all the way down, right? So these two numbers are the same. And so we can cancel those out. Okay. Anything factorial divided by itself is 1. But you can't reduce anything else like a fraction. Okay, all of the other things are not the same as you saw in the previous slide. Now we can use this a lot, right, to solve a lot of different types of problems. Right, so let's simplify these factorial expressions. Okay, so on the top we've got let's look for where's the largest numbers that we have. We've got a 7 down here, a 6 up here. Okay, so 7 times 6 factorial, okay, is 7 factorial. We can leave this 6 up here. Let's write this 5 out. 5 times 4 times 3 factorial. And that'll get rid of this one. And now we can do a little bit of division here. And we're left with 5 times 4 over 7, or just 20 over 7. Now, you guys, when in real life, when counting situations and outcomes and things like that, you should have whole numbers. Right here, we're just showing how factorials work. Okay, so just remember that when you're doing these types of counting things. Fractions shouldn't really happen. Okay, fractions when you're looking for probabilities, but when you're counting outcomes, there's only so many there can be. I did the previous example the faster way. Let me show you the longer way. and we'll just write them all out. But this is going to take just a second, but 6 times 5 times 4 times 3 times 2 times 1, that's 6 factorial. Okay, 12 times 11, 10, 9, 8, 7, 6. Just trying to show you why we use factorial notation and how helpful it can be. 13 times 12 times 11 times 10 times 9, 8, 7, 6. Now you should see how all of this is going to cancel out, just like I did in the previous example. And I'm just going to grab a different color here to show it. Okay, well, 12, 11, 10, 9, 8, all of these are going to cancel out. Right, and this was 12 factorial. This was 13 times 12 factorial. Those cancel out. So we've got a 13 on the bottom. That color's getting a little lost there. Let me change that up. Yeah, 13 on the bottom. We can cancel out these 3s, 2s, and 1s. Okay, so that takes care of our denominator. In the numerator, everything is canceled out except for 6, 5, and 4. That is 30 times 4, which is 120 over 13. So as you can see, the factorial notation makes things much simpler, much easier to deal with. You just have to understand that the exclamation point just means it's that multiplication of all those numbers in a row. It's not something that you will use a bunch in statistics or in math all the time, but it's helpful to have this little tool in your as you learn math. It pops up here and there, and it can be really useful in those cases. So let's talk about how we can count different types of things. Okay, so let's talk about first how we will count things when order doesn't matter. Okay, so let's say as part of a summer camp, you're asked to choose 4 different events from the list that you see over here. And we want to know how many different ways can we choose those 4 events. Okay, well, if we look at choices A and B here. So archery, swimming, craft, zip line, swimming, craft, zip line, archery. When order doesn't matter, right, if the order of the events doesn't matter, then A and B here are indistinguishable from one another. These are the same outcome. Right? We would count them as the same outcome if the order doesn't matter. And so they're indistinguishable from one another. And so when we count this way, we wouldn't consider these 2 things to be different outcomes. Right? You could reorder archery, swimming, crafts, and zip line, and it would all be the same outcome. And, 1, 2, 3, and 4, 2, 3, 4, and 1. Right? So long as you use it was these same 4 events, it doesn't matter which order they're in. Okay, that's all the same outcome. How many different ways can we do that? Okay, well, we could count that. When order doesn't matter, we use a formula for what's called combinations. Right? How many different combinations of those 4 events can we have? Right? Or of these 7 events can we have if we choose 4 of them? And so in this case, N represents the total, right? And R represents the number that you're choosing. And so there are 7 events to choose from, and we're going to choose 4 of them. Okay, but it doesn't matter which order we choose those 4. And so let's see. The way you would write this, and there is also a button for in your calculator for combinations and the next one as well. You may have to look a little bit to find those. But if you need some help with your calculator, I can probably help you if you shoot me an email. But the way that we write this is we're going to replace N and R with our numbers 7 and then a C for combinations. Okay, combinations again is when order doesn't matter. And so that's 7 factorial divided by 7 minus 4 factorial times 4 factorial. Okay. And so that's 7 factorial over 3 factorial times 4 factorial. Notice the parentheses here, subtract first. Okay, and so what we'll do to solve this is we're just going to go 7 times 6 times 5. And we're going to stop at the highest one in the denominator, which is 4 factorial. We're going to leave that 4 factorial in the denominator alone, because that's where we stopped. We know those two will divide out. Okay, and then 3 times 2 times 1. Oh, I wrote 3 twice. Okay, so these cancel. 3 times 2 is 6. And what you wind up with is 7 times 5, or 35. And so there are 35 different ways that you can choose those 4 different events. Or there are 35 ways you can choose 4 different events. Okay, if the order of your choices don't matter. Okay. If the order of your choices do matter, let's say there's some kind of time schedule and you want to make sure that you choose the events in the same order or something like that as a friend, and you want to predict the probability, right? You need to know how many possible ways can you do that, right? How many possible ways can you solve that, right? So here we're talking about counting when the order does matter, right? So the same events, we're going to choose 4 different events, but now the schedule matters, the way that we write them down, right? Let's say there are time slots, right? So we got to get them all in the right time slot if we want it to be the same as our friend. How many different ways could we choose them? Now, if order matters, A and B are different. These are now 2 different outcomes, and we have to think about them and count them as 2 different outcomes, right? Because they're written down in a different order, right? Because the events occur in a different order. Okay? So in this case, now when order does matter, A and B are different. So they're 2 different outcomes. So we would have to count them as 2. So whereas when we had combinations for this, right, there are only 35 if it doesn't matter what order we write them down. Okay, but now there's going to be much more if it matters which order we write them in, because here you can see just A and B are different. Right? And remember, any way you reorder them, that's each one's a different outcome. Okay, and so we call those permutations. So we use a permutation formula for that. Okay, permutations kind of refers to the reordering of those terms, right? The reordering of the A, B, C, and D, B, A, C, D, A, B, D, C, right? It's all about reordering the different events that you choose. Okay, and so again, there's a permutations formula in your calculator that will do this math for you, but let's just talk about it. Right, again, N is the total, which there are 7 events to choose from. R is the number that we're choosing, so we're choosing 4 of them. And so that's going to be 7 factorial divided by 7 minus 4 factorial, right? Or 7 factorial over 3 factorial. That's 7 times 6 times 5 times 4 times 3 factorial. Divided by 3 factorial, those cancel. 7 times 6 times 5 times 4 is equal to 840. Okay, this is also the exact multiplication I showed you guys at the end of the last video, those 4 in order. So now there's way more outcomes, right? If the order of our choices matter, there's way more outcomes. Right? Because A and B would have been different, as you saw before in the previous slide. So let's just look at a couple of examples of these. And then next week, we'll talk more about, we'll start connecting this more back to statistics. And you'll see why probabilities matter so much. So from the 12 albums released by a musician, the recording company wishes to release 3 in some type of box set. How many different box sets are possible, assuming that the order in which the albums are chosen for the box set is irrelevant? You're going to choose 3 albums out of 12 for a box set. But it doesn't matter which order you put the albums in the box, the same 3 are always going to be there. Right? And so there's only so many ways you can choose 3 to put in the box, right, before you ship it off. Once you ship it off, those 3 albums are there. It doesn't matter how they wind up in the box, right? It doesn't matter their order in the box. And so if the order doesn't matter, we would use combinations. Okay? The total we have is, here's n. We're going to be choosing 3. Okay? And so that's going to be 12 factorial over 12 minus 3 factorial divided by 3 factorial. And that's 12 factorial, 9 factorial, and 3. So again, we can reduce the top one down to the highest one in the denominator, which is 9 factorial. And then we'll just write the other one out. That's a 2. And we wind up with 12 times 11 times 10 divided by 3 times 2 times 1. 3 times 2 is 6. 12 divided by 6 is just 2. 11 times 10 is 110 times 2 is 220. So there are 220 possible different box sets you could make from those 12 albums. Okay, one more example. How many different ways can the gold, silver, and bronze medals be awarded, right, if there are 12 athletes competing? Well, now the order does matter, right? Because if we, let's say, athlete A, B, and C get gold, silver, and bronze. Well, B, A, and C, right? If athlete B got the gold instead of athlete A, right? If they switch, those are 2 different outcomes. And so now the order matters. And so now we'd use the permutations formula. We're choosing 3 again. Right, so 12 factorial divided by 12 minus 3 factorial. That's 12 factorial over 9 factorial, which is 12 times 11 times 10. That's 9 factorial divided by 9 factorial. We're going to cancel those out. 12 times 11 times 10. I might know the answer to that. That's what I thought it was. 1,320. So there's way more possible outcomes when the order here matters. So at the end of the section here, we did discuss counting, but again, we discussed counting in a slightly different way, right? Counting in ways that you don't always think about when you're trying to count things. Okay, it's not just 1, 2, 3, 4, 5 all the time. This can be helpful in other things as well, beyond just probability and statistics. But do hold on to these ideas. We won't use them all as much as we go forward, okay, but they will be helpful to understanding some of the things that we're going to do going forward. If you have any questions this week, or if there's anything I can help you with, please let me know. And next week, we'll start to talk more, I believe, about the next chapter and get into discussing how all of this probability stuff relates to the statistics we've been discussing. You guys have a great week, and I will talk to you next week.